What is up, guys? My name is Vincent, and in this video, I wanted to talk about process control. And specifically, I hope to give you guys a good introduction as to what is process control and why do we care about it, and also give you some intuitive examples to think about when you are starting a process control class as an engineer. Because before I took my process control class, I honestly had no idea what I was getting myself into, and the math got super complex, and tying it back to real world examples became pretty tricky. And so I think it's very important to first, before you dive into all these equations and formulas, just understand what are you trying to do here, and why does it matter. And so I think the very first thing that is good to talk about with all of this stuff is just imagine you're at home and you're taking a shower, and you have your shower set to some temperature, and you like to take warm showers, hopefully, and someone in another room flushes the toilet or they turn on a sink. And intuitively, what happens? And hopefully, we know that the answer to that question is because there's a drop in the flow of your cold water, but the flow of your hot water remains the same within the mixer inside of your valve in your shower. You now get really, really hot shower, and you can accidentally end up scalding someone or burning them. And so it's a big issue. And so, um, intuitively, what do you do if you have those two knobs where you see that, the your supply of cold water just was decreased? You have options. You can decrease the hot water supply, or you can increase the cold water supply, or you can decrease, or you can do some combination of the two. And this is in order to maintain some set point. You have a set point, you have a desired output of your process, which in this case would be the temperature of your shower, because you don't want to burn anybody, but you also don't want to be too cold. And so that is a very good example of what is a process control. And in that situation, you are the controller, because you are registering inputs and you're responding to those, or you're registering the outputs and you're responding to them by changing your inputs. And so a lot of stuff you're going to be talking about has to do with how can you change your inputs to maintain some set point value on an output or outputs, because in many situations you're going to have many outputs. The shower example is one where you've got two inputs, which would be your hot and your cold water supply, and you only have one output, which would be your temperature of your outlet stream after you've mixed the two fluids together. So yeah, it is very good to think about it this way, and just to remember that at the end of the day, your goal as a process engineer is to figure out how do you design the logic controllers to respond to this situation. And when we start dealing with perturbations in our inputs, and a great example of one would be one in which I turn on the sink while someone's taking a shower, I just caused a perturbation in my input into my process, which would be the supply or the flow rate of cold water. And so, how do I respond to this input or this perturbation in my input and my process? Because it will cause a change in one of my outputs, like the temperature of my outlet water. And this comes into, or one of the first controllers you're going to talk about is something called feedback controllers, which is where you will experience a change in your output, like the temperature of your shower, and then you will have a controller and some logic to determine how should you respond to this new output, this error, which is the deviation between your desired value and your current value. What do you change? How much do you change it in order to get back to your desired set point value? So, how you respond to error is a huge topic. And the two big things you care a lot about are performance and robustness. High performance systems are going to be able to keep you closer to your set point value, and they'll be able to respond more quickly. But you trade off robustness, and what we can see is that you can design controllers sometimes in which you will run into issues where they are unstable, or they'll create oscillations in your outputs that are nowhere close to what you want and your desired values. So figuring out what kind of time constants you want to go with, and I'm not going to get too deep into this just to keep this a very simple intro video, but with your PID controller, which is the gist of the logic that you have in your process, your goal here is to figure out with your PID controllers, you have three tuning parameters. And at the end of the day, as complicated as it may seem with all these numbers and formulas, your goal is to just figure out what are the optimal tuning parameter values, those three values for your PID controller. And you don't just jump directly into a PID controller up front. Generally, you'll start with a P only controller, which only has one tuning parameter, and the controller just responds proportionately to the error that you have present. But you'll learn why you need more sophisticated controllers later on. So hopefully this is making some people interested in this stuff. Um, we use it all the time in industry and all of our processes. Even if you're not a chemical engineer or an electrical engineer, you're going to be using devices every day that have these PID controls built into them so that they know how to respond to perturbations to maintain some desired set point value. Your oven is a great example. You just have all these things all over the place. And I think this is going to wrap things up for this intro video. I hope that it motivates or inspires or educates some people into what is process control all about. Feel free to ask me any questions, and thank you for watching.